this is the first time we get to orbit Mercury. NASA has finally broken its long-held silence on the latest findings from the James Webb Space Telescope. This groundbreaking discovery, hidden from the public eye until now, centers on the planet Mercury. Mercury's searing surface and volatile atmosphere have piqued people's attention and aroused speculation for decades, providing a harsh but alluring window into the extremes of planetary formation. However, nothing could have prepared us for the discoveries made by the JWST. The findings, now corroborated and confirmed, are nothing short of revolutionary. What the JWST detected on Mercury's surface has opened a Pandora's box of cosmic mysteries. This anomaly hints at the possibility of advanced processes at work, processes that could rewrite the history of not just Mercury but also our understanding of our solar system. What has NASA discovered exploring Mercury? Join us as we explore how NASA finally breaks its silence on the James Webb Telescope discovery on Mercury. It seems like Mercury, sitting so close to the Sun, should already be a dead planet. Experts predicted that the little rock, which is only slightly larger than the Moon on Earth, would have been ravaged by the Sun's powerful radiation to the point of desolation. The temperature differential between the planet's day and night sides is about 1,100 degrees Fahrenheit, making it an extremely inhospitable environment. Mercury, however, has shown to be a complex and paradoxical environment full of surprises that scientists underestimated. Interesting data suggests that Mercury is more than just a dry rock. Mercury, one of the 5 planets visible to the human eye from Earth, has been known to humanity for thousands of years. Mercury was probably noticed by ancient civilizations long before written records were preserved, therefore, the exact date of its discovery is unknown. Mercury was named after the messenger god of the same name by the ancient Greeks and Romans, who were among the first civilizations to examine the planet thoroughly. The planet Mercury was associated with the Greek god Hermes, who was believed to be in charge of communicating between the gods due to the speed with which the planet moved across the sky. The subsequent centuries saw a proliferation of astronomical research on Mercury, with scientists learning ever more about the planet's characteristics and habits. In the early 17th century, Johannes Kepler made a very important discovery related to this. Kepler made the first accurate observation of Mercury's irregular, rather than circular, orbit around the Sun. As new tools and methods for studying the planet emerged in the 19th and 20th centuries, additional important findings regarding Mercury emerged. 2 missions have successfully reached the swift planet thus far, and the third, Bepi-Colombo, is scheduled to arrive in late 2025 and is being carried out by the space agencies of Japan and Europe. Despite the limited scope of these ground-based studies and on-site excursions, they have been crucial in dispelling many of our initial misconceptions about Mercury's enigma. Mercury may be small, yet it packs a big punch. Although its diameter is barely larger than the Moon's, Mercury is over 4 times as massive as Earth's natural satellite. In fact, Mercury is the second densest planet in our solar system after Earth. The planet's extreme density comes from the fact that it has a large iron core that makes up about 60% of the planet's volume. In contrast, Earth's core by volume is only about 15%. The abnormal internal structure has spawned several theories on Mercury's birth. The outer layer of Mercury may have been melted or dispersed by the solar winds in its early stages, according to scientists. Another possibility is that the young planet was hit by a massive impact that severed its outer, more delicate covering, exposing its inner, more robust core. It appears that the impact may not have been a direct hit but rather a sideways swipe that preserved a portion of Mercury's primordial crust and mantle, given that these components are still detectable today. Mariner 10, the first mission to visit Mercury, discovered that the planet retains a magnetic field. Upon launch in 1973, scientists were taken aback by the finding since they had anticipated that a planet of this size would have cooled down quickly and its interiors would have solidified, rendering it completely devoid of global magnetism. The presence of a magnetosphere implies that part of Mercury's core is still churning. Mercury's magnetic field is about 100 times weaker than Earth's on their respective planetary surfaces. The sluggish dynamo means that the planet is at the tail end of its developmental stage, on its way to becoming a dead planet like Mars. In the 2010s, the second Mercury mission, Messenger, documented that the planet's magnetic field was off-kilter. The magnetic South Pole doesn't sit on the geographic South Pole, instead, it is buried almost at the center of the planet. According to Antonio Genova, an aerospace engineer and planetary geodesy and geophysics student at Rome Sapienza University, the planet's magnetic field provides a window into its innards and a record of its past, suggesting the extent to which the planet's whirling core has slowed down over the course of billions of years. In order to delve deeper into Mercury's hidden mysteries, his team will take advantage of the ongoing BepiColombo return mission. Meanwhile, Mercury has such a thin atmosphere that it doesn't really qualify as an atmosphere. This ethereal gas layer, which is so rarefied that it hardly registers pressure readings, is instead referred to as an exosphere by scientists. The exosphere of Mercury must constantly replenish itself from the surface due to the continuous solar beatings it receives. Astronomers have been able to observe atomic sodium, potassium, and calcium in Mercury's exosphere since the 1980s. These metals have strong emission signals that may be seen from Earth using telescopes. In common parlance, these metals aren't gases, however, they reach Mercury's atmosphere through solar particles and meteorites that crash into the planet. A radiant tail behind Mercury, stretching 15 million miles in length, is formed when gases and particles ejected from the Sun interact with each other in the exosphere. The length of this tail changes from season to season as Mercury moves closer or further from the Sun. If you were standing on Mercury and looking up at the right time of the year, Mercury's long tail would appear in the sky as a faint orange glow, as if the heavens were illuminated by sodium street lights. A planet perched right at the Sun's mole shouldn't harbor any water, let alone ice, right? However, a barrage of radar signals was pointed toward Mercury in the 1990s by researchers at the Arecibo Radio Telescope in Puerto Rico and the Goldstone in California. Two highly reflective areas, most likely ice deposits, were noticed by the crews near the poles, which came as a complete surprise. Could Mercury's close orbit around the Sun help the planet generate ice? Although it seems contradictory, recent research into the chemistry of Earth's surface has raised the possibility that heat-generated ice actually exists. Ice can form in craters that are shaded from the Sun. Even though Mercury can reach temperatures of up to 750 degrees Fahrenheit throughout the day, surface temperatures there are roughly -330 degrees Fahrenheit as they are exposed to space. For over 10 years, data from the now-defunct Messenger mission informed us of this ice. However, the explanation for how some of the ice got there, chemically speaking, remains under investigation. A new study shows how water can collect on the surface even amid these extremely hot temperatures. This is not some strange, out-of-left-field idea. The basic chemical mechanism has been observed dozens of times in studies since the late 1960s, but that was on well-defined surfaces. Applying that chemistry to complicated surfaces like those on a planet is groundbreaking research. Surface minerals of Mercury include hydroxy groups, which are combinations of oxygen and hydrogen atoms. Since the planet's magnetic field is insufficient to deflect the solar wind's protons, these charged particles are prevalent on Earth's surface. Protons are positively charged subatomic particles. According to this study's model, they can travel across Mercury in response to a magnetic field where they can subsequently implant themselves in the soil and hydroxy groups. The hydroxy groups collide because the Sun's intense heat energizes them. Water itself, composed of hydrogen and oxygen in varying amounts, is produced by these impacts. Additionally, excess hydrogen is liberated and floats above Mercury's surface. Some of the water molecules are dissolved into their elemental components when exposed to sunshine. Some of the water molecules sink to the surface while others float off into space. Some water molecules, though, manage to evade these doomsday scenarios and instead crash into Mercury's poles, where they form shadowed craters that will remain there indefinitely. Since Mercury lacks a substantial atmosphere, one that could transport heat, for instance, the molecules can remain there. The accumulation of water ice would be quite significant, even though this process seems minor at first. According to the model, Mercury is projected to amass 11 trillion tons of water ice in 3 million years. This amounts to around 10% of the planet's observed ice. Other ice may have arrived from small worlds such as asteroids, comets, and meteorites. Mercury is not alone in having ice on its surface, as water ice has also been discovered on the Moon and small worlds such as asteroids and comets. Nonetheless, the rates of water deposition at these sites may differ. the process in our model would not be anywhere near as productive on the Moon. For one, there's not enough heat to significantly activate the chemistry. Earth and the other terrestrial planets in our solar system have had their water supplies dispersed all around the planet by natural phenomena like weather cycles. If scientists want to sample ancient ice in its pristine form in the solar system, the best source is probably Mercury's poles. Mercury defied expectations again when MESSENGER detected volatiles on the sun-scorched world. Chemicals that can undergo a rapid phase transition from solid to the search for extraterrestrial life has always fascinated humanity, and the possibility of finding life-supporting planets enhances this interest. Mercury, the closest planet to the Sun, has long been a subject of mystery and intrigue. Recent discoveries have shed light on some of these mysteries, particularly regarding the planet's craters and volatile substances. Researchers have found glacier on Mercury, which help explain the peculiar depressions in many craters. These depressions were likely filled with volatile substances that were released into the atmosphere upon impact and then dissipated. How these unstable layers formed remains an open question, but evidence from Mercury's North Pole suggests that these volatiles were deposited in a fully developed terrain. Scientists speculate that Mercury's early atmosphere might have collapsed, depositing these substances, or that the planet once had lakes, as theorized by Jeffrey Cargill. He proposed that Mercury's volcanic core could have released dense, extremely salty steam that eventually dissipated, leaving the salt behind. Further studies are needed to explore what lies beneath Mercury's surface. Mercury also has unique ground features known as hollows. These irregular depressions were first glimpsed by Mariner 10 in 1975 and later photographed in detail by the MESSENGER spacecraft. Hollows vary in size, from a few dozen feet to over a mile across, and can be as deep as 120 feet. They appear similar to the soft, airy insides of a sourdough loaf when cut open. Scientists believe that volatiles are responsible for the formation of these hollows. Since Mercury lacks an atmosphere, surface features like hollows are not created by rain or wind but by the ground leaking volatiles into space. Unlike Mercury's ancient impact craters, hollows are much younger, averaging around 100,000 years old, and continue to develop. Interestingly, Mercury is the only planet with these features, as similar pockmarks do not appear on any other celestial body in our solar system. Further structural features on Mercury include chaotic terrains, large sections of the landscape fragmented by what looks like a mess of Jenga pieces. Some scientists believe these terrains form due to unstable soils losing structural support and collapsing. Others think chaotic terrains result from asteroid impact ripples wrapping around the planet and meeting on the opposite side. Mercury's volcanic activity history is another intriguing aspect of its terrain. MESSENGER confirmed earlier observations by Mariner 10, revealing that Mercury's surface is covered in shiny plains of lava that have smoothed over older craters and ridges. This volcanic activity likely stopped between 1 billion and 3.5 billion years ago. However, another type of volcanism, involving explosive eruptions, has also been observed. These explosions suggest the presence of ancient pyroclastic volcanoes that collapsed. Scientists believe that subsurface volatiles, expanding as they rise to the surface, caused these volcanic explosions, akin to an overinflated balloon bursting due to gas pressure. Understanding Mercury's volatile substances is crucial for space exploration. Mercury has an unusual chemical composition, with a higher concentration of thorium compared to its neighboring planets. Using spectrometry, scientists have determined that Mercury's thorium content is closer to that of Mars, which formed at cooler temperatures further from the Sun. This has led to speculation that Mercury might have formed farther from the Sun and was initially much larger, possibly the size of Earth. Since no probe has landed on Mercury's surface, scientists rely on other sources of information, such as meteorites, to test these theories. Some meteorites, called orbites, share chemical elements with Mercury, suggesting they could be remnants of an interplanetary collision that displaced Mercury. Although this idea is debated, it offers a fascinating hypothesis about Mercury's origins. Geochemical analogues, Earth rocks with structures similar to those found on other planets, provide additional evidence. By studying these analogues, scientists can form hypotheses about the origins of extraterrestrial rocks. For example, Cyprus, a crustal fragment that erupted from the Tessis Ocean around 90 million years ago, was studied and found to have rock compositions identical to those measured on Mercury. This discovery added valuable information to our understanding of Mercury, making Cyprus the first terrestrial counterpart for the planet. Further studies of these rocks may reveal more about the geological processes that occurred on Mercury. The Bepi-Colombo mission, a collaboration between the European Space Agency and Japan, is expected to provide even more insights. Launched in October 2018, Bepi-Colombo has already made 3 flybys around Mercury and will make its final approach in 2025. The spacecraft will split into 2 orbiters, one measuring the magnetic field and the other studying the surface and internal composition. These orbiters will provide detailed data on Mercury's mineral compositions, topography, and interior structure. Comparing this data with past mission results might reveal whether Mercury is still geologically active and help scientists understand the planet's enigmatic origins. The study of other celestial bodies also offers valuable insights. For instance, the James Webb Space Telescope has observed signs of a carbon-rich atmosphere on 55 Cancri E, a fiery exoplanet classified as a rocky super-Earth. This exoplanet, twice the diameter of Earth, orbits its star at a mere 4% of the distance between Mercury and the Sun, with a surface likely covered in molten magma. Despite its extreme conditions, JWST data suggests that 55 Cancri E has an atmosphere, likely a secondary one rich in carbon dioxide or carbon monoxide. This discovery challenges previous assumptions and highlights the dynamic nature of exoplanetary atmospheres. As Bepi-Colombo continues its mission, it may soon reveal more about Mercury and its potential connections to other celestial bodies. These observations are crucial for understanding our solar system's history and the processes that shaped it. The quest to uncover the origins and characteristics of planets like Mercury not only enhances our knowledge of the cosmos but also offers glimpses into the possible conditions for life beyond Earth. The study of Mercury and its mysteries remains a key theme in space exploration, contributing to our broader understanding of planetary science and our place in the universe.